Physical geodesy aims to determine the level surfaces of the Earth's gravity field. Today, we are going to learn about a specific gravimeter which applies both the concepts of geodesy and electrical engineering, the superconducting gravimeter, and how it works. Let's start off with gravimetry. Gravimetry is the measurement of gravitational field strength. Its units of measure in SI is in meter per second squared, hence the term acceleration due to gravity. So how do we measure gravitational field strength? By using a gravimeter. It has two types, absolute and relative. So what's the difference between the two? Absolute gravimeters uses a free-falling mass to measure gravity. It is done by counting and timing the interference fringes, and then the acceleration of the mass can be measured. Relative gravimeters, also known as spring-based gravimeters, measures only relative gravity in accordance with the response of a spring wherein the difference in gravity is measured between two locations. The ideal spring gravimeter, also known as superconducting gravimeter, has the best sensitivity relative to the other gravimeters. Now, a superconducting gravimeter is the name of the game. It was developed by Goodkite and Prothero at the University of California, San Diego in the late 1960s. The superconducting or cryogenic gravimeter is based on the levitation of a superconducting sphere in a stable magnetic field created by current superconducting coils. Superconductors are materials that have exactly zero electrical resistance and expulsion of magnetic flux fields, working only in a very low temperatures. It is capable of detecting gravity variations as small as 0.1 nanometer per second squared, about the size of a diameter of an atom. Due to its high sensitivity and low drift rate, the superconducting gravimeter is eminently suitable for the study of geodynamical phenomena through their gravity signatures. So how exactly does a superconducting gravimeter work? Other relative gravimeters are based on a test mass that is suspended by a spring. The mechanical aspects of a spring suspension causes erratic drift that is difficult to remove. The superconducting gravimeter solves the drift problem by replacing the mechanical spring with the levitation of a test mass using a magnetic suspension. There are three major superconducting elements. First, we have the levitated test mass, which is a 2.54 cm diameter sphere which is made of niobium that weighs about 5 grams. A displacement transducer is formed by a capacitance bridge that surrounds the sphere. Second, the field is generated by two niobium wire coils superconducting below a temperature of 9 Kelvin that carry perfectly stable and persistent superconducting currents to provide an extremely stable magnetic field with no resistive losses. And lastly, we have a superconducting shield which is used to exclude the Earth's magnetic field from entering the space where the sensor is housed, since it would seriously degrade the magnetic levitation stability. The superconducting elements are maintained by a liquid helium bath at 4 Kelvin and a cryogenic refrigerator. This is how a superconducting gravimeter generates gravity reading. At the start, an extremely stable magnetic field is generated by two niobium wire coils. When current is trapped in coils, currents are induced on the surface of the sphere. As with the currents in the coils, the induced currents are perfectly stable. The levitation force is produced by the interaction between the magnetic field from the coils and the currents induced on the surface of the superconducting sphere. A point is initialized where gravity is known. The levitating mass is perfectly centered. Then, the gravimeter is transferred to an unknown point where measurement is done. At the new point where the gravity is different, the levitating mass is not perfectly centered. There is a corresponding current which will revert back to the center. the current in the coils can be precisely adjusted to balance the force of gravity on the sphere at the center of the displacement transducer. The corresponding current has an equivalent delta G. The ratio of currents in upper and lower coils is adjusted so that the magnetic force gradient or spring constant is very weak. As a result, a very small change in gravity gives a large displacement of the test mass. This allows for the instrument to achieve very high sensitivity. Studies of Earth dynamics in general use superconducting gravimeter. An example is a study by Sachi Shiomi entitled Testing Gravitational Physics with Superconducting Gravimeter. This relative gravimeter is the most accurate one. The accuracy is brought upon by electrical engineering concepts. Thank you for watching!